Hello and welcome to this revision session for AQA A-Level Physics on paper 2. So in today's revision session we're going to be looking at how to answer examination questions on A-Level Physics paper 2. So if we are successful and we learn in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision? So when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the question in the revision session. When you're doing this, make sure to write your answers in full sentences and show your full working out, whilst in the right hand side write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. At the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising A-Level Physics? So the first step is learning the key facts, understanding the knowledge of the course. So use your revision guides, class workbook, prep notes and textbook to learn the key ideas of the course, and you may wish to make mind maps or write out notes yourself. The second stage should be retrieval, testing yourself. So use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. And then finally, the last step is to practice examination style questions. So use exam prep books, homework books, supervised study books and additional workbooks to answer exam questions and mark your own work, and you may wish to download your own past papers to do this. So the three steps of learning the key facts, then testing yourself and then practicing exam style questions are how you should be revising A-Level Physics. So let's now have a look at answering some questions on the topics from paper 2 in A-Level Physics. So the first questions are going to be on gravitational fields. So the following question says, the lines in figure 4 show the shape of a gravitational field around two stars, G and H. Compare with reference to figure 4 the masses of G and H, and then X and Y are 2 points in the field. Annotate figure 4 to show the field direction at X and the field direction at Y. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you've got to remember that in a field, that the density of the field lines indicates the strength of the force, and in this case the gravitational force is affected predominantly by the mass of the object that is present. So you can see that G must have a greater mass than H does, and why is that? Because there's two things you could possibly say. You could possibly indicate that the density of the field lines is greater around G compared to H, or you could say that the null point, the point at which the two gravitational fields will cancel each other out, is closer to G than it is closer to H than it is to G, so therefore G must have a stronger field than H. Now again, the other fact you've got to remember about gravitational fields is that the field lines point in the direction a point mass would take. So therefore, for both of them, it would indicate towards the actual object. Because it's a gravitational field, it's always an attractive force that's going on for gravity. So therefore, the masses will always be going towards the two objects. So therefore, the field lines should be pointed towards the actual object. And it's important that they're given tangential arrows as well. Now the next question says, a spherical asteroid P has a mass of 2 × 10 to the 20 kilograms. The gravitational field strength at its surface is 0.40 newtons per kilogram. Calculate the radius r of P. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, if you look at your equation sheet given for your examination, you are aware that you can work out the gravitational field strength little g by doing little g equals big G m over r squared. So we can therefore rearrange this and make r the subject by saying r is equal to the square root of gm over g. You've then got the value of the gravitational constant from your equation sheet, you've got the value of the mass in the question, and you've got the gravitational field strength little g in the question as well. So you pop in all the values, you work it through, and you get 1.8 × 10⁵ meters. The next question says, sketch on figure 5 the variation of the gravitational field strength G with distance r. The distance r is measured from the centre of P, and then explain what is represented by the area under the graph between r equals r and r equals 2r on figure 5. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, it's important to note that you should be aware that for these objects that the gravitational field strength will vary as a radial field, so therefore it's going to be sketching across like so. Now again, you'll be aware that as the distance doubles, well therefore the field strength is going to go down by a factor of 4 because it's related to r squared. So when one is double, the other is gone by the power of 4. Now we know that at a distance of r that the field strength is 0.40 from the previous question, so therefore at 2r it's going to be 0.4 divided by 4, so it's 0.1, and then you can do for 3r, so then you can divide that by a factor of 4 as well, okay, so you can work it through like so. Sorry, that would be for 4r. For 3r, what you would do is you go from r to 3r, you then go by a factor of 9 because it's 3 squared, so it'll be 0.4 divided by 9, which is 0.044. So you can plot those points in there and sketch the line in. Now, what is represented by the area? Well, again, there's a couple of answers you could say. So you've got to be aware that in these graphs that the area under the line represents the energy transferred or the work done per unit mass, or that is, in essence, the gravitational potential. So therefore, if we can think it in terms of energy per unit mass, it's the energy transferred or work done on an object per unit mass to move from r to 2r. Or you could say it's the increase in gravitational potential moving from r to 2r. Again, remember how to work out values from graphs. The next question says, asteroid P approaches the two stars G and H. Figure 6 shows one position of P close to H. The gravitational force on P from G is 6.38 times 10 to the 12 newtons. The mass of H is 3.00 times 10 to the 25 kilograms, and the mass of P is 2.00 times 10 to the 20 kilograms. The distance HP is 1.50 times 10 to the 11 meters. Calculate the magnitude of acceleration of P. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, you know straight away that it's worth 4 marks. It's going to be either a double step calculation or a challenging calculation that you're given. Now you have the gravitational force, you have the mass of two objects, and you have the distance between the two. So what you can therefore do straight away is say F equals GMM over R squared. So what you can then do is work out that value of the force. So you can find the force between P and H. So therefore you can say, well, the force between P and H is 6.67 times 10 to the minus 11 times by 3 times 10 to the 25 times by 2 times 10 to the 20 all over 1.5 times 10 to the 11 squared. So therefore gives you an answer of 1.8 times 10 to the 13 newtons. So what we've got here is we've now got the two components of the gravitational force, the one from P to G and the one from P to H. So as a result, we can work out the total by using a bit of Pythagoras and saying that the total is going to be FPH squared plus FPG squared, all square rooted. So we do those two and we square both values, add them and square root them to get the total value of F to be 1.9 times 10 to the 13. At that point we know acceleration. Well, we've got the masses, we know the force, so we therefore know acceleration is the overall force divided by the mass. We've just worked out the overall force to be 1.9 times 10 to the 13. We can then divide it by the mass, which is 2 times 10 to the 20, to get our answer to be 9.4 or 9.5 times 10 to the minus 8 meters per second squared. We're now going to have a look at some questions to do with the electrical fields topic. So figure 7 shows two identical negative point charges, QA and QB, in fixed positions 8 millimeters apart. O is a point midway between the charges, P is a point 3 millimeters away from O, and equidistant between QA and QB. Firstly, the resultant electrical field strength at P is 1400 newtons per coulomb and towards O. Calculate the charge of QA. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, a couple of things. Firstly, what do we know that the equation is for the resultant electrical field strength? Well, we know from the equation sheet that E is equal to Q over 4 pi epsilon 0 R squared. But what we also know is from our setup, from our diagram, we can also say that the resultant electrical field strength is going to equal 2E cos theta. So what we can do is we can work out what E is going to be by using that equation of Q over 4 pi epsilon 0 R squared. We can then link that into we can work out from the equation of E resultant is equal to 2E cos theta. We can therefore link that into work out E, and therefore what we can do is we can then work out one of the charges by using that equation E equals Q over 4 pi epsilon 0 R squared to work out our value. So you can work that all through using trigonometry to work out what cos theta is going to be, and then you can work it out and you get Q equals 3.2 minus 3.2 times 10 to the minus 12 coulombs. The next question says, sketch on figure 8 the variation of electrical potential V with displacement x from O between QA and QB. Calculations and numerical values of V are not required. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to be aware that the electrical potential will always be a negative value, and that's a very important idea because they're attracting each other. So at that point, we know it's going to be a negative value. So at that point, there's going to be a smooth curve, which is always negative, and there's going to be a non-zero maximum at the y-axis, and it's going to be asymptotic at about 4 and minus 4. The next question says, figure 9 shows a point R between O and QB. QA and QB are fixed positions. A small mass M with a negative charge Q is released from rest at R. Only electrostatic forces act on M. After release, M oscillates about O along the line between QA and QB. State and explain how the direction of the resultant force on M varies during oscillation. Describe the energy changes of M from its release until it reaches O for the first time, and then deduce whether or not M performs simple harmonic motion. So pause the video now, then unpause the video when you want to go through your answer. Right, so this question is a very standard question for paper 2 because it links two topics together, the electrical field strength and simple harmonic motion. So you should know for the first one, state and explain how the direction of the resultant force on M varies with the oscillation. Well, the direction is always acting towards O. That's because the idea that the Q charges will both repel M, and therefore the nearer it is to Q will repel more, so therefore it will always be attracted to O. Now, in terms of what's happening, it's going from electrical potential energy because it's moving due to the repulsion in the charges. Okay, so it's transferring to kinetic energy because it's now moving due to this repulsion. Now, again, to get that second mark, you've always got to indicate how the energy changes will take place. So a decrease in electrical potential energy will be equal to an increase in the kinetic energy. So when it goes from one store, it will go towards the other store. Now, the last one, will it perform simple harmonic motion? Well, this is actually a link to the idea of what simple harmonic motion is. So simple harmonic motion comes from the idea that the acceleration is directly proportional to the displacement in the opposite direction. Now, you should know that the electrical field strength and the electrical force will link as 1 over r squared. So therefore, it's not going to be directly proportional to distance because it's over distance squared. So therefore it will not be simple harmonic motion. We're now going to look at questions on the capacitance topic. So the first question says, state what is meant by a capacitance of 37 millifarads. Then a capacitor is made up of two parallel metal plates which are separated in air by a distance d. A cell of negligible internal resistance is connected across the capacitor as shown in figure 10. Switch S is closed and the capacitor becomes fully charged. While S is still closed, the plate separation is reduced to d over 2. State and explain what happens to the magnitude of the charge stored by the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this first question? Well, this first question, you've got to learn how to just define what we mean by capacitance. So capacitance is the charge stored per unit volt. Now in this case it's 37 millifarads, so therefore it's 37 millicoulombs stored per unit volt, or per 1 volt. Now in the next question, what's going to happen to the magnitude of charge stored by the capacitor? Now again, you've got to link it to the equation. Now the equation for capacitance is that capacitance is going to be equal for a parallel plate capacitor to E0 ER A over D. Now again, we can consider E0 and ER to be the same value in this instance because we're not changing any of those terms, so therefore capacitance is going to be linked to A over D. Now again, we know that Q is equal to CV, so we know straight away that the capacitance has doubled. We know that the potential difference or the voltage has stayed the same. We're told that from the question, so therefore Q must have to double because we're linking it into therefore that separation. You can see how they all link together in their different equations. Now the next question says, explain how charge is conserved when the plate separation is reduced. S is now opened. The plate separation is increased to D. And state and explain how the energy stored in the capacitor changes during this process. And then explain how energy is conserved when the plate separation is increased as described in the previous question. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? So, in this first question, you've got to understand that charge is conserved because there's an equal number of electrons removed from the positive plate as deposited onto the negative plate. Remember the idea that there's always two plates. One is where the electrons are removed, okay, and they are the ones from the positive plate, and the electrons are going onto that negative plate. Now, what's going to happen in the next question? So again, what will we do? Well, we know again that charge is going to stay the same because the capacitor is isolated, or that the charge can't flow because the switch is now open, so the charge can't flow around the circuit. So at that point it tells us that the capacitor halves because we know that the capacitance halves because you know E equals Q squared over 2C. So therefore at that point we can tell that energy doubles. So you can even say this qualitatively, but you can't get enough marks for this. The idea that work has to be done to that external system, to the capacitor, to separate out that plus and minus plates, so therefore energy must be stored in the capacitor because we're putting energy into it to actually separate those two plates out. So we know that from the previous one that links into the equations. Now how is energy going to be conserved? Well, the idea of energy is conserved because the gain in stored energy is provided by work being put into the capacitor to separate the plates apart. So work is being put in, energy is being put in to that capacitor to actually physically separate those two plates from each other because they are attracting each other. Let's now have a few questions on thermal physics. So the first question says the volume of a fixed mass of gas is kept constant. Explain why the pressure of the gas decreases when the temperature is decreased. Then show that the pressure P of an ideal gas can be given with the equation P equals rho RT over M, where rho is the density, T is the absolute temperature, and M is the molar mass of the gas. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? So you've got to talk very qualitatively about what is going on. So the idea is that if we decrease the temperature, the internal energy of the gas will decrease, because for a gas, that the internal energy for an ideal gas is the thermal energy. It is linked to the temperature. So therefore, what we can say is that the mean kinetic energy, or the speed of the particles, will decrease. So therefore, if the particles are moving slower, the frequency of the collisions with the container, okay, now remember it's the frequency of the collisions, not just the collisions themselves, the frequency of the collisions will therefore decrease. So therefore the change of momentum that's occurring will decrease, and we know that that force is equal to change in momentum over time. So therefore if the change in momentum decreases, the force exerted will decrease, so therefore the pressure will decrease, because we know pressure is force over area. The area is unchanged, the force is reduced, the pressure goes down. Now the next question links to a lot of the previous equations you know for thermal physics. So we know that the number of moles is equal to m over m. We know that rho is equal to m over v, and we know that PV equals nRT. So what you need to be able to do is link those into the equation. So what you can do is start with PV equals nRT. We can then sub in m over m for n, or we can sub in that v is going to equal m over rho. The two small m's will cancel through. We've then got the big M left in the equation. As you can see, we've got rho left in the equation. We can rearrange to make P the subject, and we get out our value. The next question says, figure 3 shows the variation of pressure with temperature for a gas at a constant volume. The density of the gas is 1.6 kilograms per meter cubed, and assume that the gas is ideal, determining kilograms per mole the molar mass of the gas. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you consider answering this particular question? Well, when you're given a graph, you've got to be able to use it. So use a data point from the line of best fit, which is linking, as you can see, the pressure and the temperature. But you'll notice from the equation given, from the graph given, that the pressure is in megapascals, so you have to convert that, and the temperature is in degrees Celsius. Now, the ideal gas equation needs the absolute temperature, so you need to convert from degrees Celsius into Kelvin. So what you'll do is you'll convert the temperature into Kelvin. You'll convert the pressure into pascals. We'll then use our previous equation of P equals rho RT over M. We know R from the equation sheet because it is just a gas constant. We know rho from the information given in the question. You are told it. We've read off T and M from the graph, and therefore we can work it out to be 3.9 times 10 to the minus 2. Another way in which you can do it is you can determine the gradient of your graph, and you'll be aware that the gradient is going to be equal to rho R over M, because we know that it's pressure over temperature, which from the previous equation we can work it through. So we can then use that to work out what our value of kilograms per mole is going to be. Let's now have a look at some questions on the topic of magnetic fields. So the first question says, a student investigates the EMF induced in a coil of wire when it is rotated at a constant angular speed in a uniform magnetic field. An oscilloscope is connected across the output of the coil. Figure 1 shows the trace on the oscilloscope screen, and figure 2 shows the time-based setting for the oscilloscope. Firstly, describe what the student should do to determine an accurate value for peak EMF induced in the coil. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important you understand how to work out values accurately from an oscilloscope. So what you're firstly going to have to do is work out what the number of each vertical square means in terms of volts. So you can look on the right hand side and you can see that is in fact for the time base, so that's not going to be relevant in this case. However, what we can do is we can work out what the value is by looking at what our Y gain is going to be, our Y scale. Then what we can do is turn off the time base, and then what you can do is increase the Y gain or decrease like the volts per division setting, the Y gain, so the trace takes up more of the screen, so it's easier to read off the value. At that point you want to work out the most accurate value. Now in science, in physics, to reduce your percentage uncertainty, to increase the accuracy, you want to take the largest value possible, and that reduces that value. So as a result, the largest value possible is not the peak voltage, but in fact it's the peak to peak voltage, the value from the top of the line to the bottom of the line. So you'd work out your peak to peak voltage and then divide by 2 to get that most accurate value. The next question says, show that the angular speed of the coil is approximately 13 radians per second using figure 1 and figure 2, and then figure 3 shows the oscilloscope screen with the time base set to off. The student wishes to make an accurate measurement of the time period of the induced EMF. Calculate an appropriate time base setting and explain your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So how to work out the angular speed is you work out the number of squares for the multiple cycles, and then what you can do is you can therefore work out like 9.6 to 10 squares for 4 cycles. So therefore what we can do is work out the number of squares for 1 cycle. We can then work through by saying that the angular speed is 2 pi over t. So therefore we know 2 pi because it's just a number. We know t because we can work it out from the previous question, because we can work out the time needed for 1 period. Okay, again, it's more accurate to take multiple values and then divide by the number of values that you take to reduce your percentage uncertainty. So you should get an answer from about 12.7 to about 13.1 radians per second. Now again, the answer for this next one should be about 50 milliseconds per division, because what you want is you want your 1 cycle to fill the entire screen. So you've got to think, how would you work it through to get 1 cycle in there? So it's going to be that 50 milliseconds value from the information given in the previous question. The next question says, the peak EMF is 7.5 times 10 to the minus 2 volts. The coil has an area of 6.0 times 10 to the minus 3 meters squared and 25 turns of wire. Calculate the magnetic flux density of the magnetic field. And figure 4 shows the coil connected to a 27 ohm resistor. The resistance of the rest of the circuit is negligible. Calculate the mean power dissipated in the resistor. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you should know from the equation sheet that the maximum induced EMF, the peak EMF, is equal to BAN omega. Now in the previous question we just worked out omega. You have got the value of area in the question and the value of N. So at that point we have peak EMF, we have A, we have N, we have the angular speed, so you can work out what B is, and we get 0.039 Teslas. Now in this next question again, what are we aware of? We've got the resistance, we know it's 27 ohms. Okay, and what we also know is we can actually work out what our value of V is. But because it's an AC generator, you've got to remember, or an AC motor, what you've got to remember is you've got to be using the value of VRMS, because you use VRMS and IRMS to work out values in alternating current circuits. So the first thing to do is work out VRMS. Now we have peak EMF or V0, so we can say VRMS is V0 over square root 2. That's again an equation given to you on the equation sheet, and at that point we can sub that into the next equation of P equals V squared over R. We've got R, we've just worked out V, so it's 1.0 times 10 to the minus 4 watts. So now what we're going to do is we're going to look at answering questions on nuclear physics. So the first question we're now going to look at is that a proton of 0.675 MeV of kinetic energy collides and fuses with a stationary nucleus of boron-11. An excited carbon-12 nucleus is produced. The excited carbon-12 nucleus de-excites to a stable carbon-12 nucleus by emitting a gamma photon. Calculate in MeV the energy of this gamma photon. Assume the carbon nucleus does not recoil when the gamma ray is emitted, and state your answer to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So the first thing to note is you can see that from our equation we've got a proton and we've got the boron, and that then turns into the carbon nucleus, or the carbon-12 nucleus. Okay, so the first thing we need to do is add the proton rest mass to the mass of the boron, and at that point we can work out what our mass defect is, or the difference in the masses between that and carbon-12, and then at that point we can then multiply our rest mass, or the mass defect, which we have probably in U, by 931.5 MeV. Again, that's a conversion factor. You've just got to learn how to convert between U and MeV, which is by multiplying by 931.5, and at that point we've got our energy in MeV. We can then add the kinetic energy contribution by the proton, which we're told in the question is 0.675. So at that point we get 16.6 MeV, and again we give our answer to 3 significant figures. Why is that? Because if you look in the question, the number of significant figures given for energy in this question is 3, because it's 0.675. So we give our answer to the same number of significant figures as the value given in the question, which is 3. So therefore it is 16.6 4.6 MeV. The next question says, an alternative mode of decay for carbon-12 is to decay into beryllium-8 nucleus and an alpha particle. The carbon nucleus is initially stationary and the beryllium-8 nucleus and the alpha particle move as a result of the decay. Compare the momentum of the kinetic energy of the beryllium nucleus to the momentum and the kinetic energy of the alpha particle immediately after the decay. Ensure to support your answer with a calculation. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to be aware that we need to conserve momentum in this particular collision, in this particular production. So therefore we know the carbon nucleus is initially stationary, so the positive momentum of one must equal the negative momentum of the other. So therefore we can say that the momenta are equal in magnitude yet opposite in direction. So at that point we know that the momentum calculation is that the velocity, therefore if the momentum is the same for both, well then the velocity of the alpha particle must be 2 times the velocity of the beryllium. We see that because we know that the mass times velocity of both must equal each other, and we know that that the mass of the beryllium is double that of the alpha particle from the information given 8 and 4. So at that point we know the velocity of the alpha must be double that of the beryllium. We know that kinetic energy is a half mv squared. Now we know that the mass of the beryllium is twice as much as the mass of the alpha, yet the kinetic energy, so the velocity of the other is twice as much as that. However, the velocity is squared, so one goes up by a factor of 2, the other goes up by a factor of 4, so therefore it'll cancel out to be a factor of 2 increase from the kinetic energy of the alpha compared to the kinetic energy of the beryllium, because that velocity is squared. The next question says, one alpha particle with 2.9 MeV of kinetic energy rebounds from a different stationary carbon-12 nucleus. Show that the closest separation between the alpha particle and the carbon-12 nucleus is approximately 6 femtometers. Then the nuclear radii was initially estimated using the technique of closest approach of alpha particles. Electron diffraction experiments give more accurate determination of nuclear radii. Suggest why. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So what you've got to do is you've been given the kinetic energy to be 2.9 MeV. Now we then, because we want to work out values in meters later, need to have this in SI units. The first thing we need to do is convert MeV to joules. We know that the conversion from EV to joules is 1.6 times 10 to the minus 19. So therefore the conversion from MeV to joules is going to be 1.6 times 10 to the minus 13, because we've got 10 to the 6 from the M. So at that point we can get our energy to be 4.64 times 10 to the minus 13 joules. And therefore we now want to work out our separation. Now we know that the work done is that's 4.64 times 10 to the minus 13, and we know for the electrical fields that the work done is going to be equal to Q times by potential, so therefore it's going to be equal to Q1 Q2 over 4 pi epsilon 0 r. We can therefore make r the subject because we know the charge of the alpha particle, it's going to be 2 times by 1.6 times 10 to the minus 19. We know the charge of the carbon nucleus because there's 6 protons there, so it's 6 times by 1.6 times 10 to the minus 19. So we can work out our values to be 6 times 10 to the minus 15 meters. Now this next question, you've just got to be aware of how you determine the nuclear radii. So the idea is that a small de Broglie wavelength, or a de Broglie wavelength of comparable size to the nuclear radius, will allow you to determine the radius size easily. However, the closest approach method depends on the kinetic energy of the alpha particle, which will affect how close it can get to the nucleus before it will be repelled. So therefore the closest approach, you've just got to know this, provides an upper limit to the size of the nuclear radii, because the alpha particle will not physically touch the outer part of the radius. It'll be repelled by its electrical charge repulsion, so therefore it will be an overestimate. Now the next question says, define the binding energy of a nucleus and then calculate the binding energy of a nucleus of thorium-232. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this question you've just got to be aware of the definition of binding energy. So the definition of binding energy is the energy required to separate a nucleus into its individual nucleus. Now the next question, you've got to then use the information given to work out what this binding energy could possibly be. So you know for a fact that you got a proton number of 90 and then a neutron number of 142 because it's 232 minus 90. We can then work out the mass of the protons by multiplying it by the mass of the proton, which is given to you on the equation sheet, and multiplying that value of 142 by the mass of the neutron given to you on the equation sheet. You can then find the difference in mass between those two values and the mass of the thorium nucleus, which is given in the question. You've then got your mass defect, and therefore you can turn this into an energy, and now you've got your mass in kilograms, so therefore you can work out your energy by doing E equals mc squared to get 2.9 times 10 to the minus 10 joules. So this next question says the thorium-232 nuclei absorb neutrons and become uranium-233 nuclei after a series of radioactive decays. Deduce the proton number and the nucleon number of R. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to be aware that when you have absorbing a neutron, well, you're going to increase your neutron number, but not your top number, okay? And you've got to be aware that with the beta decay, you're going to not change the top number, but you're going to increase the value in the bottom by 1. So what you can see here is that if you're going to conserve the numbers for R there on either the middle line or the bottom line, well, therefore the proton number needs to be 91, because from the middle line, 90 equals 91 minus 1, and then again on the middle line we know the value is going to be 233 because 233 equals 233 plus 0. The next question says uranium-233 nuclei undergo neutron-induced fission. One possible fission reaction is shown below. Table 2 shows the binding energy per nucleon for each nuclide. Calculate in joules the energy released in the fission reaction. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So what you've got to do is you've got to work out the binding energy for each of the values by multiplying the binding energy per nucleon by the number of nucleons for each of the values, which is given by the top number for each one. So you work out the binding energy for each one of those values and you get them in MeV. You then got to find the difference between the neutron and the uranium, okay, which is the starting nuclei, and the exon, the SR, and the 3. Remember, there's 3 of them, 3 neutrons, because that's the products afterwards. And then at that point, you find that difference, okay, which is expected to be 182.33 MeV. Then you can convert that into joules by using your conversion factor, which is 1.6 times 10 to the minus 13, as explained before, to get your answer to be 2.9 times 10 to the minus 11 joules. The next question says, when a large number of nuclei of uranium-233 undergo fission, the average energy released per fusion will be different to your answer in the previous question. Explain why. Then the critical mass of uranium-233 is 16 kilograms, so that the radius of a sphere of uranium-233 of critical mass is approximately 6 centimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question you've got to be aware that different fissions will produce different types of nuclides, and these different nuclides will have different binding energies per nucleons, which will give a different difference in binding energies, which will give a different energy released. Now in this next question we've been given our density and we know what the critical mass is, so we know density and mass, so we can work out the volume by doing density is equal to mass over volume. Now therefore we can use the idea that the radius is that the object, the nucleus, is a sphere, because it tells us that in the question. So we know that the volume of a sphere is 4 over 3 pi r cubed. So at that point we can work, we've got V from the equation density equals mass over volume. We know 4 over 3 because it's a number and pi because it's a number, so we can work out what r is going to be, and we get 5.9 times 10 to the minus 2, which is approximately 6 centimeters. The next question says, this ratio of surface area to volume for a 3D dimensional object is sigma, where sigma equals surface area over volume. So determine sigma for the sphere in the previous question, then explain why a cylinder of uranium-233 with a mass of 16 kilograms is unable to sustain a fission chain reaction. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question you've just got to be aware of how you can link the surface area and the volume for a sphere. So we know that the surface area is 4 pi r squared, and we know that the volume is 4 over 3 pi r squared. So we can cancel out the values of 4, we can cancel out the pi's, we can cancel out 2 of the r's present, so we therefore get that sigma is going to be 3 over r, and then at that point we know what the value of r is from the previous question, so we can work it out there to be about 50. Now the next question is explain why it can't sustain a fission chain reaction. It's the idea that we need on average for a sustained chain reaction 1 neutron on average per fission event to then go on to lead to another fission event taking place. Now the idea is if you've got a large surface area, most of those neutrons produced in the fission events will leave the actual object without causing another fission event because it's less likely to hit another nucleus. So at that point the fewer neutrons will induce less fission, so at that point there'll not be enough neutrons produced to lead to a one-to-one fission event each time, so it cannot maintain that fission process. The next question says, define the activity in the context of radioactive decay. Then a dice roll experiment models radioactive decay. The standard 6-sided dice are used. One dice represents one radioactive nucleus, and at time t equals 0 there are n0 dice. The dice are rolled, and the dice showing 6 dots on the top surface are removed as shown. The number of n of remaining dice is counted. The process of rolling, removing and counting the dice is repeated at intervals of 1 minute. In this experiment, the variation of n with time t can be modeled mathematically with n equals n0 e to the minus lambda t. Explain why lambda is approximately 0.2 minutes to the minus 1. So pause the video now, then unpause the video when you want to go through your answer. Right, the first thing is you've just got to know what the definition of activity is, which is the number of nuclei decaying per unit time per second. It can't be per second, it's per unit time. So it's the number of the nuclei that decay in a particular time. Now how is this value for lambda going to be 0.2 minutes to the minus 1? Well, we know that on average when you roll a dice and there's no loading of the dice, that one dice in 6 will actually roll that value of 6 dots, so therefore the chances getting that is 0.17 is removed each minute for every one dice. So therefore what you can do is you can work it through by doing that you can say that you work it through to be 0.16, so therefore it's going to be roughly 0.2. Now the next question says estimate the time t at which n equals n0 over 2, and then say this experiment is done with n0 equals 500. Estimate using the mathematical model for the variation of n with time t, the time t at which n equals 20, then explain why the actual time taken may be significantly different to your estimate in the previous question. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So you should know that n over 2 is going to be 1 half-life, because that's what the definition of half-life is, the time it takes to drop from n to n over 2. So we can therefore look at our equation sheet and see that half-life is equal to log 2 over lambda. So what we can therefore say is we know that lambda from our previous question is going to be 0.17 or 0.12. So at that point we do log 2 over that value of 0.17. So therefore we can work it out to be 3.8 minutes or 4.2 minutes if you use the actual value that is given precisely, which is 0.17. Then the next one is we sub in our values to n equals n0 e to the minus lambda t. We've then got to rearrange it, and we've got to make t the subject. Again, remember, if you want to take an exponential down to be a common term in your equation, you've got to use natural log. So we would say that natural log n over n0 is equal to natural log e to the minus lambda t. So that natural log and e will cancel through. So we know that natural log n over n0 is going to be equal to minus lambda t. So therefore we can work out what t is after we've done that. We know what n is okay, which we know to be, so we know what n is and we know what n0 is, because you know n is 20 from the question, n0 is 500, so you can work it all through. Remember that we got our decay constant lambda in terms of minutes, or minutes to the -1, so if you keep it in that value, we'll get our answer in time in minutes, so you work it all through and we get 19 minutes. Now, why will this be significantly different? Well, if you think about it, from the question we're told, if you look on here, we've only got about 500 dice. So that's only a really small number of dice, and rolling dice is a completely random event. We've assumed that it's going to be equal probability, but we don't particularly know that, so therefore it's different to decay processes, because rolling of dice is also a discrete event, and the rolling and whilst the decay is happening continuously, so therefore it might be completely different. So that brings an end to our revision session today. If we've been successful in our revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So thank you very much for watching this revision session on Physics Paper 2 for AQA A-level physics. Thank you very much and have a lovely day.